Within our chapter on miscellaneous TLS topics, we are in the midst of investigating the difference between the master secrets, pre-shared keys, and encryption keys, and the pseudorandom function PRF, and the HMAC-based key derivation function HKDF. The protocol design of TLS then fundamentally evolves around the goal to have the client and the server authentically agree on these secrets, from which the keys used to protect the application data exchanged later on can be derived. In this lesson, we will now investigate the relationship between the master secret, pre-shared key, and encryption keys within TLS 1.3, where this relationship is given by the HMAC-based key derivation function HKDF. The ultimate goal of TLS 1.3 is to have the client and the server arrive at keys which can be used to encrypt and authenticate the data exchanged within various stages of the TLS connection. TLS 1.3 then doesn't just provide means to encrypt the application data exchanged after the handshake, but TLS 1.3 also provides means to encrypt early zero round-trip client data sent by the client together with its client hello message, and TLS 1.3 also provides means to encrypt handshake messages as early as possible. Within TLS 1.3, the keys used to encrypt and authenticate data are derived with the HMAC-based key derivation function HKDF, which is defined in RFC 5869 and which we will have a close look at on the next slide. The starting point is the derivation of a so-called early secret, which is a secret derived with HKDF from either a pre-shared key or an all 0-byte string in case no pre-shared key is used. HKDF is then again used to derive a client early secret, which would then be expanded into the encryption keys and initialization vectors used by the client to encrypt early zero round-trip client data. The derivation then continues into the derivation of a handshake secret from the early secret, which incorporates the result of the ECDHE key exchange conducted, or in case no ECDHE key exchange was conducted, the derivation of the handshake secret simply incorporates an all 0-byte string. HKDF is then used to expand the handshake secret into a client handshake secret and a server handshake secret, which then form the basis for the derivation of encryption keys and initialization vectors used by the client and the server to encrypt their respective handshake messages. Finally, the master secret is derived with HKDF from the handshake secret, and from the master secret, the client application secret and the server application secret are derived, which then now form the basis for the derivation of the encryption keys and initialization vectors used by the client and the server to encrypt their respective application data messages. You may have noticed that I repeatedly just mentioned the use of encryption keys, but didn't mention anything about a specific authentication key, as for example TLS 1.2 fundamentally requires to have derived as well. In contrast to TLS 1.2, TLS 1.3 now makes exclusive use of authenticated encryption with associated data ciphers as provided by AES GCM, AES CCM, and JAJA20 Poly 1305, and as such, TLS 1.3 doesn't require a separate HMAC-based authentication, as the AEAD ciphers take care of authenticity, and as such, TLS 1.3 only has to derive keys for the AEAD ciphers. Last, a server during a TLS 1.3 connection can then at any point indicate that a resumption secret derived with HKDF from the master secret can be used as a pre-shared key in future connections. That's then pretty much it. The derivation tree outlines the relationship between the pre-shared key, the early secret, the handshake secret, the master secret, and the encryption keys. And from this derivation tree, we can see that the link between these secrets and keys is given by the HMAC-based key derivation function HKDF. It's now clear that this HMAC-based key derivation function HKDF is of highest importance to TLS 1.3, so let's have a closer look at it. The HMAC-based key derivation function HKDF is specified in RFC 5869 and serves the purpose of deriving cryptographically strong keys from an initial source of keying material. HKDF then consists of two modules. The first HKDF module is an extraction module used to extract a fixed length pseudorandom key from input key material. The second module of HKDF is then an expansion module which expands the fixed length pseudorandom key into a pseudorandom key block of any desired length. The HKDF extraction module is then really just HMAC, where the cryptographic hash function used for HMAC is the cryptographic hash function indicated by the cipher suite, and with TLS 1.3 would then either be SHA-2 with 256-bit hash values or SHA-2 with 384-bit hash values. The HKDF expansion module is then a repeated application of HMAC, where as many HMAC results are concatenated as needed to get the desired length of the output key material. As with TLS 1.2, I find it instructive to exercise an example, and the example I chose are the key derivations required for the TLS 1.3 cipher suite TLS AES 256 GCM SHA-384. For this cipher suite, both the client and the server require a 256-bit AES key for the encryption of the application data. With this cipher suite, HKDF then uses HMAC SHA-384, and as SHA-384 produces 384-bit hash values, the HKDF expansion module needs to only be used once each by the client and the server on their respective application secrets in order to obtain their respective 256-bit AES key. That's it. This is all I wanted to say regarding the TLS 1.3 early secret, handshake secret, master secret, pre-shared keys, encryption keys, and the HMAC-based key derivation function HKDF. I personally think that the cryptography of TLS 1.3 is very beautiful, and hopefully I managed to capture some of this beauty with this lesson.